let me just get right to it. I want to bring in a point that I think is relevant here from the standpoint of all the sample collection we're going to do. And as I'm a geochronologist, I'm going to present this in the context of geochronology mostly, but I think this is relevant for all the sample collection. And then I'm going to talk a little bit about what I think are the key things that we need as far as samples are concerned. So from this slide, the key point I want to make is that we're interested in making some broad-scale geologic observations here that reflect the global evolution of the moon and as it pertains to the Earth and the rest of the solar system. And we're going to be analyzing samples that are the size of our thumbs. And so there's a large extrapolation here, and this is a tricky business. And I've tried to outline two different ways this is done with different levels of success. So if you look at the slide, the upper arrow represents the first pathway. We've collected a bunch of samples from Apollo. They're from a limited area. One of the samples we got from 15 was a Genesis rock, which is a pharaonanorthosite. Was analyzed mineralogically, and it was discovered to have very high abundances of, plagioclase with very high abundances of calcium and mafic minerals that were very depleted in magnesium. And so it was realized fairly early on that this was an evolved product of a magmatic system. At the same time, going to the next panel to the right, we realized from some of the surveyor missions, and as represented here by the Clementine mission, that the surface of the moon is covered with pharaonanorthosites of the like of 15415. And so the supposition here was that the magma body we were talking about was global in scale and the moon was likely to have a magma ocean. So this is a success story. Now I'll show you something where we can actually get into a little bit of problems here. So one of the rocks going on the lower set of arrows here on the bottom part of this figure, again, we collected from Apollo 16, which was 60025. It had similar characteristics to other pharaonanorthosites in being calcic rich and magnesium poor. However, because we have to do chronology on this thing, we need fairly equal abundances of the two minerals that are present, pyroxene and plagioclase, which makes it a little bit of an atypical rock. We completed an age on this, and we got something like 4.37 billion years. And then we're left with, what does this age mean? In one interpretation, you assume that this rock represents a product of a global magma ocean, and so we're dating the age of the pharaonanorthosite formation of the global magma ocean. However, because this one sample is a rather unique sample and having lots of pyroxene in it, it could also represent some unique sort of thing. And so and might lead to something like a serial magmatism type model. So we have a problem of extrapolation that I think we need to think about when we're collecting samples. So can I have the next slide, please? So here's another example of this. This is a samarium neodymium plot of the isotopic composition of basaltic rocks that were collected at the Apollo sites. This has been done multiple times in the last 25 years. We've all basically gotten the same result. A line regressed through this, has a slope corresponding to about 4.33 billion years. It indicates that this is the time when these rocks were all in equilibrium. However, because the samples are from a limited site, one interpretation suggests that they're part of a magma ocean solidification. Another idea is that it might reflect overturn and localized melting on the near side. It's also been suggested that this reflects impact-induced melting on the near side. If you look at the slide to the right, we've plotted pharaonanorthosites that have been collected predominantly at 16, and they fall in that same isochron. And because they're from a different location, this provides more indication of what this actual basaltic chronology might mean. It suggests that the pharaonanorthosites and the basalts both have to be produced by a single process, and as a result, this more likely flavors the solidification of a magma ocean. So I just throw that out as an example of how we have to look at these samples when we're trying to extrapolate to global scale processes. So can I have the next slide?
Lars, are you within a minute or so?
Yeah, so okay. One more slide.
Yep.
Next slide. So here's some things we need to do here. So we need lots of samples. We need samples from outside the PKT because this is how we will extrapolate them. The samples need to be large because right now our problem is that we don't get big enough samples to make the measurements that we can make properly, and our techniques have not evolved in the last 20 years significantly. Final slide. Okay, so some things to keep in mind for chronology. Most chronology doesn't work on lunar samples. They're extremely difficult to date, and I've listed a variety of reasons here. To understand the age of a sample, it must be dated by multiple chronometers. One chronometer doesn't define an age because these samples are basically bimineralic. They're all mixing lines. And so the question is, does the mixing line have chronologic significance? And that requires multiple chronometers. We need to address global processes. We need multiple suites of samples because the isotopic systematics of the suites defines these things, like I showed you in the first two slides. And finally, the point that I can't emphasize enough is the ages must be interpreted in the context of petrology. And so little tiny chunks of samples are not as useful as bigger things. And these samples need to be selected with somebody's eye on them, not just making a measurement, but to see how much impact melt is there, how brecciated it is, how friable it is. These are the critical questions. We don't care so much about what the compositions are or even what the mineralogy is. It's the textures of the samples that dictate the chronology. Thank you.